Hello everyone. Today we deals with unit number 6, that is complex analysis. Especially we focused on complex differentiation, complex integration and conformal mapping in this unit. But before going to complex differentiation and integration, we revise some basic definition and properties from complex number. So what is complex number? So any number z which is of the type x plus iy is called as complex number, where x and y are real numbers and I is square root minus 1, and that x is called as a real part of z and y is called as imaginary part of z. Now if y is 0, then z is equals to x is called purely real number, while if x is 0, then z is equals to iy is called purely imaginary number. If z is equals to x plus iy is given complex number, then its conjugate is denoted by z bar and it is given by x minus iy. Means we just interchange the sign of imaginary part. Then if z is again a complex number which is given by x plus iy, then mod of z is denoted by either mod z or r, and it is given by square root of x square plus y square, that is square root of real part square plus imaginary part square. Similarly, we can define argument of z, that is amplitude of z, theta, and it is tan inverse of y by x, tan inverse of imaginary part of z divided by real part of z. Now once we define this modulus r and argument theta, we can convert complex number z in terms of r and theta. We call it as polar form of complex number. So polar form of complex number is z is equals to r e raised to r theta. So we already defined r and theta. One more important property for z and z bar: if z is equals to x plus iy and z bar is x minus iy, then the product x plus iy into x minus iy becomes x square plus y square, which is mod z square. So these are some basic and important properties for defining complex differentiation and integration. Now before defining complex differentiation, just sake of completeness, we define complex valued function, because if you directly define derivative of complex number is some constant number and therefore its derivative becomes 0, so it is meaningless, and therefore we have to define complex valued function. So any function which having complex variable z is called as complex valued function. So that is f of z is equal to some u plus iv, because z is complex, so f of z is also complex, so it looks like some real part plus I times some imaginary part u plus iv, where u and v are function of x and y. So afterwards we replace or we denote z is equals to x plus iy as a complex number, and f of z is equals to u plus iv as a complex valued function. For example, if f of z is sin z, so sin z means sin x plus iy, so we can convert this function in the form of u plus iv. So applying sin a plus b formula, it is sin a cos b plus cos a sin b, and further we know that cos of iy, it is cos hyperbolic y, and sin of iy, it is I times sin hyperbolic y, and therefore we can easily get values of u and v. Now complex differentiation, once we define this complex valued function, what is derivative of f of z with respect to z? So it is similar to real valued function. In simple words, all the properties of differentiation of real valued function is applicable for complex valued function. For example, if f of z is sin z, then its derivative d by dz of f of z is cos z. If f of z is 3z square, then its derivative with respect to z is 6z. Now once we define this properties of complex differentiation, next and very important definition is analytic function. It is also called as holomorphic function. So any function f of z which is of the type u plus iv is called analytic if it is well defined and has derivative at each point in given domain. So what do you mean by well defined function? So well defined function means for every finite value in given domain it gives finite value in same domain again. uh, for example, f of z is equals to z. It is very standard function. It is called as identity function. It is analytic everywhere. But f of z is equals to 1 by z. It is not analytic. By simple observation, if you replace z by 0 in that, we get infinity. So for finite value, we get infinite, and therefore it is not defined at z equals to 0. Now, very important topic, that is Cauchy-Riemann equation, CR equation. It is necessary condition to check whether given function is analytic or not. It is just a necessary, not sufficient. Uh, so for any complex valued function, f of z is equals to u plus iv, where u and v are function of xy. The equations partial derivative of u with respect to x is equals to partial derivative of v with respect to y, and partial derivative of u with respect to y is equals to minus times partial derivative of v with respect to x are called as Cauchy-Riemann equation, CR equation, and any function which satisfies this equation is analytic. Now, how to remember these equations? So suppose u and v are two functions, u is first, v is second, and x and y are two variables, x is first variable, y is second variable. Then partial derivative of first with respect to first variable is equal to partial derivative of second function with respect to second variable. So it is direct relation. And if you take cross first function with respect to second variable and second function with respect to first variable, then there is negative sign. If given function is in polar form, means r theta form, then CR equations are dabba u by dabba r is equals to 1 by r times dabba v by dabba theta, and dabba v by dabba r is equals to minus 1 by r times dabba u by dabba theta. So this CR equations are very important to check whether given function is analytic or not. So for example, f of z is equals to z square, and question is show that f of z is analytic everywhere. Analytic everywhere means analytic in complex plane. So we start with given function f of z equals to z square, and we know that z is x plus iy, so it is x plus iy square. So using a plus b bracket square expansion formula, it is x square plus 2i xy plus iy square, but we know that I square is minus 1, so it is simply minus y square. Now separating real and imaginary part, so x square minus y square is the real part plus I in bracket 2xy, so 2xy is the imaginary part, means u is x square minus y square and v is 2xy. So finding out their first order partial derivatives, so u with respect to x is 2x, u with respect to y, partial derivative of u with respect to y is minus 2y, v with respect to x is 2y, and v with respect to y is 2x. So by simple observation, u with respect to x is same as v with respect to y. First function with first variable is equals to second with second, 2x, and u with respect to y is minus times v with respect to x, means CR equations are satisfied, and therefore given function is analytic everywhere. Similarly, we can check for cos z. So again, replace z by x plus iy first, then applying cos a plus b formula, it is cos a cos b minus sin a sin b, then cos of iy is cos hyperbolic y, and sin of iy is I times sin hyperbolic y. So we can easily identify u and v. Real part is u, imaginary part is v with negative sign. So find out their first order partial derivatives. U with respect to x, derivative of cos x is minus sin x, cos hyperbolic y as it is. Then u with respect to y, cos x as it is, derivative of cos hyperbolic y is just sin hyperbolic y. Same for v, finding out v with respect to x, it is minus cos x sin hyperbolic y, and v with respect to y, derivative of sine hyperbolic y with respect to y is cos hyperbolic y, keeping minus sin x as it is. So again, by simple observation, we get u with respect to x is equals to v with respect to y, and u with respect to y is equals to minus times v with respect to x, means CR equations are satisfied, and therefore given function cos z is analytic everywhere. Now next definition is harmonic function. So any function phi of xy is called harmonic if it satisfies Laplace equation. Laplace equation means sum of second order partial derivatives is equals to 0. So delta square phi by delta x square plus delta square phi by delta y square is equals to 0, or we can write it as phi x x plus phi y y is equals to 0. Note that if f of z is equals to u plus iv is an analytic function, then u and v both are harmonic, very important, and that u and v are called as harmonic conjugate of each other. So there is always one question based on this harmonic conjugate in your final examination. Either u or v are given to you, and question is find out harmonic conjugate. Now the last theoretical topic from complex differentiation is Milne-Thomson method, and it is very important method to convert given function f of z in the form of z. So what we do, we simply substitute x equals to z and y equals to 0 in given function. So it converts given function in the form of z. That is Milne-Thomson method. Now we solve some problem based on harmonic function and harmonic conjugates. So for example, show that u is 2xy is harmonic and also find its harmonic conjugate, that is v. So let us begin with u, and we know that u is harmonic if and only if it satisfies Laplace equation, that is delta square u by delta x square plus delta square u by delta y square is equals to 0. So for that purpose, we find out partial derivative of u with respect to x, which is 2y. If we differentiate it one more time partially with respect to x, it becomes 0 because there is no x in first order derivative. Similarly, u with respect to y is 2x and there is no y, therefore second order derivative of u with respect to y becomes 0, and hence delta square u by delta x square plus delta square u by delta y square is equals to 0, means u is harmonic. So this is proof of first part. Now in second part, we have to find harmonic conjugate of u, means v. So again, we start with the first order partial derivative of u with respect to x and u with respect to y, that is 2y and 2x. Give its equation number 1. Now to convert this function of u or derivative of u in the form of v, we apply CR equation. So applying first CR equation, that is u with respect to x is equals to v with respect to y. So from equation number 1, we get v with respect to y is equals to 2y. So we have value of partial derivative of v with respect to y is equals to 2y. Delta v by delta y is equals to 2y. So how we find value of v from it? So we have to integrate it with respect to y, but since it is partial derivative, we have to keep x as a constant. So on integrating with respect to y, keeping x as a constant, we get v is equals to 2 times y square by 2 plus, instead of saying c as constant of integration, we add f of x as a constant here, f of x as a constant of integration, because we keep x as a constant, so that constant may be a function of x. So this is value of v, but it is not a final because f of x is unknown, so we have to find that value. So to find out f of x, we apply second CR equation, and for second CR equation we required delta v by delta x. So differentiating partially with respect to x, we get delta v by delta x is equals to, there is no x in y square or given function, therefore 0 plus derivative of f of x with respect to x is f dash of x. Suppose it is equation number 3. So according to second CR equation, u with respect to y is equals to minus times v with respect to x. So already we calculate u with respect to y in equation number 1. So it is 2x, and therefore we get f dash of x is equals to minus 2x. So on integrating with respect to x, we get f of x is equals to x square plus minus x square plus c, and hence from equation second, value of v is y square minus x square plus c, where c is constant of integration. So this is harmonic conjugate of u. Second problem, find harmonic conjugate of v is equals to sin x into cos y, and also find f of z in terms of z. Now it is little bit different. V is given, we have to find its harmonic conjugate, means u, and f of z in terms of z means somewhere we have to apply Milne-Thomson method. So let us begin with v. So v is given, therefore we find its first order derivatives. V with respect to x is cos x cos hyperbolic y, and v with respect to y is sin x sin hyperbolic y. Suppose it is equation number 1. Now to convert that v in the terms of u, we apply first CR equation again. So according to first CR equation, u with respect to x is equals to v with respect to y, and therefore from first equation, u with respect to x becomes sin x into sin hyperbolic y. So on integrating with respect to x, obviously keeping y constant, we get u is equals to minus cos x sin hyperbolic y plus f of y, and again f of y is constant of integration. Now to find out that f of y, we apply second CR equation, which is u with respect to y is equals to minus v with respect to x. So we have to differentiate u partially with respect to y. So differentiating u partially with respect to y, we get gamma u by gamma y is equals to minus cos x into cos hyperbolic y plus f dash of y. Give its equation number 3. So again comparing this 3 with 1 according to second CR equation. So u with respect to y is minus times v with respect to x, and therefore we get minus cos x cos hyperbolic y plus f dash of y is equals to minus cos x cos hyperbolic y. So on both the sides same functions are there, so get cancelled, and therefore f dash of y is 0. So on integrating, f of y is simply constant. So substitute this value in u, we get u is equals to cos x sin hyperbolic y plus c, which is required harmonic conjugate of v. Now u and v are known, we have to find f of z in the form of z. So we know that f of z is always of the type u plus iv. So substitute values of u and v. So u is cos x sin hyperbolic y plus c, and I into v is sin x cos hyperbolic y. But question is, find f of z in terms of z. So how to convert this function in terms of z? So obviously we have to apply Milne-Thomson method, that is replace each x by z and y by 0. Therefore f of z becomes cos z sin hyperbolic 0 plus c plus I times sin 0 into cos hyperbolic sin z into cos hyperbolic 0. But we know that sin hyperbolic 0 is 0 and cos hyperbolic 0 is 1. Using formulas, sin hyperbolic theta is equals to e raised to theta minus e raised to minus theta by 2, and cos hyperbolic theta is e raised to theta plus e raised to minus theta by 2, and therefore required function is f of z is equals to c plus I times sin z. Next, now it is third type of problem. Instead of u or v is given, find out harmonic conjugate. Now it is u plus v is given, and question is find out f of z in the form of z. So we firstly find out partial derivative of u plus v with respect to x and y. So differentiating this partially with respect to x, we get ux plus Vx is equals to derivative of e raised to x is e raised to x cos y plus sin y as it is. It is equation number 1. Here ux represent partial derivative of u with respect to x, Vx represent partial derivative of v with respect to x. Similarly, on differentiating partially with respect to y, we get u with respect to y plus v with respect to y is equals to e raised to x as it is, derivative of cos y is minus sin y and derivative of sin y is cos y, equation second. Now we have two equation in ux vx uy vy, but by CR equation we can convert second equation in the form of ux and vx again. So applying CR equation, which is ux is equals to vy, u with respect to x is equals to v with respect to y, and uy is equals to minus vx. So from second equation we get minus vx plus ux is equals to e raised to x in bracket minus sin y plus cos y, equation number 3. Now observe carefully, equation 1 and 3 are in the form of ux and vx. So add that equation 1 and 3, we get 2 times ux is equals to e raised to x in bracket 2 times cos y, and therefore ux is e raised to x cos y. Similarly, if you subtract equation 1 and 3 or equation 1 from 3, we get value of vx in similar way. Now we have both the values of ux and vx. So we substitute that in derivative of f of z with respect to x. So we know that f of z is equals to u plus iv. So if you differentiate it partially with respect to x, since u and v are function of xy, so we can differentiate it. So partial derivative of f of z with respect to x is ux plus I times vx, and ux and vx are known. So substitute that value here from a and b. So partial derivative of f of z with respect to x is equals to e raised to x cos y plus I times e raised to x sin y. So applying Milne-Thomson method again, replace x by z and y by 0, we get derivative of f of z with respect to z is equals to just e raised to z, because if you replace x by z, we get e raised to z into cos 0, cos 0 is 1, and plus I times e raised to z into sin 0 is 0, and therefore d by dz, derivative of f of z with respect to z is equals to e raised to z. Now in previous step we write partial derivative, and in last step we write total differentiation, because in second last step given function f of z is function of xy, and in last step we convert that function in terms of z only, so it is single valued, and therefore we write d by dz of f of z. Now on integrating we get value of f of z. So f of z is e raised to z plus something constant of integration, which is required function in terms of z. Now next and very important example, show that analytic function with constant modulus is always constant. So given function is analytic. So suppose f of z is equals to u plus iv, which is standard function, is an analytic function, and also given that its modulus is constant, means mod of f of z is constant. So what is mod of f of z? It is square root of real part square plus imaginary part square, means square root of u square plus v square, it's constant, it is given. So if square root u square plus v square is constant, we can say that u square plus v square is equals to c or c square. So it look like previous type of example, u plus v is given, find out f of z in terms of z, but here we have to show f of z is constant, means u and v should be constant. So on same line we differentiate this red color equation with respect to x partially first. So we get 2u dA by u by dA by x plus 2v dA by v by dA by x is equals to 0, derivative of constant term is 0, and dividing throughout by 2 we get u into dA by u by dA by x plus v into dA by v by dA by x is equals to 0. Suppose it is equation number 1. On same line, differentiating partially with respect to y, we get u with respect u into w by y plus v into v by y is equals to 0. Equation second. Now to convert equation second in the form of partial derivative with respect to x, we apply CR equations. So by CR equation, w by x is equals to v by y, and w by y is equals to minus times v by x. So substitute these values in equation second. So first term of equation second becomes minus u into v by x and plus v into w by x is equals to 0. So we get everything in terms of x. Now observe carefully equation 1 and 3. So each and every term is in terms of partial differentiation with respect to x. So it is very easy to eliminate that term. So squaring and adding equation 1 and 3, it gives u into w by x plus v into v by x square plus minus u into v by x plus v into w by x square is equals to 0. Now using regular expansion formula a plus b square, we expand these terms. So it is first term square plus 2 times first term into second term plus second term square. So applying that formula, we get this big equation. Now just focused on that red color part, so that both terms are equal with opposite sign and therefore get cancelled. So after cancelling that term, remaining terms are u square w by x square plus v square v by x square plus minus u square means just u square v by x square plus v square into w by x square equals to 0. So from first and third equation, from first and third term, take u square common, and from second and last term take v square common. So we get u square in bracket w by x square plus v by x square. Similarly plus v square in bracket w by x square plus v by x square equals to 0. Now again observe carefully, bracket is same in both the term, so we can take outside, and therefore we get u square plus v square into w by x square plus v by x square equals to 0. So it implies that product of two term is 0, means one of that bracket should be 0. So either u square plus v square is 0, or second term w by x square plus v by x square is equals to 0. So case number 1, suppose u square plus v square is 0, but we know that u square and v square, these are square terms, and square term never negative, and therefore their sum should be positive always, and hence u square plus v square equals to 0. It is possible only if u is 0 and v is 0. So if u and v are 0, f of z, which is u plus iv, it becomes 0, and we know that 0 is a constant number, therefore our aim is achieved, means f of z is constant function. Now case second, w by x square plus v by x square equals to 0. On same line, sum of two positive term, square term is positive, so sum of two positive term is 0, is possible only if that terms are 0. So it implies that w by x equals to 0 and v by x equals to 0. So integrating partially with respect to x, we get u is equals to some constant and v is equals to some another constant, c1 and c2, and therefore f of z becomes c1 plus I times c2. But we know that I is also some constant, so c1 constant, c2 constant, I is constant, so we get f of z as a constant. So in both the cases, we proved that f of z is constant, and hence this is proof of this example. If given analytic function is having modulus constant, then that function is constant. Now in similar line, next problem is show that analytic function with constant amplitude is also constant. So instead of constant modulus, now amplitude is given, and we know that if f of z is equals to u plus iv is the analytic function, then its amplitude means its argument theta is equals to tan inverse imaginary part upon real part, that is tan inverse v by u is constant. So this is given. So if tan inverse v by u is constant, we can say that tan inverse v by u is equals to c, and therefore v by u is equals to tan c. But c is constant, so tan c is also constant. So again, we differentiate this red color equation partially with respect to x and y. So if we differentiate it partially with respect to x, as u and v are function of x, we have to apply u by v formula. So it is upon u square, u as it is, derivative of v with respect to x minus v as it is, derivative of u with respect to x equals to 0, which implies that u into dabba v by dabba x minus v into dabba u by dabba x is equals to 0, equation number 1. On same line, differentiating partially with respect to y, we get u into dabba v by dabba y minus v into dabba u by dabba y equals to 0, equation 2nd. Now again same logic, we convert equation 2nd in the form of partial derivative with respect to x using CR equation. So by using CR equation, u with respect to x is equals to v with respect to y, and u with respect to y is equals to minus times v with respect to x. Equation 2nd becomes u into dabba u by dabba x plus v into dabba v by dabba x equals to 0. So observe carefully, our first equation is in terms of partial derivative with respect to x, and third equation is also in terms of partial derivative with respect to x. So squaring and adding 1 and 3, we get u into dabba v by dabba x minus v into dabba u by dabba x square plus u into dabba u by dabba x square, u into dabba u by dabba x plus v into dabba v by dabba x square is equals to 0. So again using expansion formula a plus b bracket square, we get this big equation. Then same line again, the red color part are same with opposite sign, so get cancelled, and from remaining term take u square common, we get dabba u by dabba x square plus dabba v by dabba x square, and take v square common, we get dabba u by dabba x square plus dabba v by dabba x square equals to 0. So again bracket is common from that both terms, so take that bracket outside, so we get u square plus v square into that bracket is equals to 0. So product of two term is 0, means either first term is 0 or second term is 0, which implies either u square plus v square is 0 or second bracket, that is dabba u by dabba x square plus dabba v by dabba x square equals to 0. So again we get two cases. So suppose u square plus v square is 0. So already we discussed about it, sum of two positive term is 0, which is possible only that terms are 0, that is u is 0 or v is 0, and v is 0, and that means f of z is 0, which is constant. Case second, if dabba u by dabba x square plus dabba v by dabba x square is 0, which implies dabba u by dabba x is 0 and dabba v by dabba x is equals to 0. So on integrating, we get u is equals to c1 and v is equals to c2, and therefore f of z is equals to c1 plus I times c2. But c1, c2, I all are constant, we can say that f of z is constant, and hence in both the cases we proved that if analytic function f of z with constant amplitude is given, then that function is constant, f of z is constant. So this is about complex differentiation. In next session we continue with complex integral part. Thank you.